90-degree bond, so the interactions become much weaker, and then these higher nematic phases or octupolar phases become important. Yeah, we haven't looked at that here, but because at this point even the stronger ferromagnetic phase has not been observed, and it would be good to see that first.
I'm a little bit confused about your phase diagram for the two-sides model in the plane over 2/2 and the lambda over 2 for the two-sides model. Yeah. Yeah. So if you have no U is 0, still you have so for the magnet.
Well, no, our analysis is not reliable there. We are really focusing on it's most reliable in this atomic picture when U is large. That's why I sort of shaded the regime which is most reliably captured by this method. Yeah, you typically go into metallic phases once U is small. And then, you're in a different regime. Yeah.
So in your exact diagonalization, you get J2 in the case of U.
There are higher J's as well. Yeah. Yeah. So ask me a question. Sorry.
Okay. Then in your case, your exact ground state shows J2 in the case of U. Am I right?
Yeah, okay. No, but as I said, this part, I'm kind of focusing on an atomic picture. When you put in this atomic picture is hugely perturbed once I go to this regime. So it's best to focus, really the description starts here. And this is the, T is 0, and then I'm really perturbing with hopping. That's the best way to think about it. And that hopping is, as I turn on hopping, I go across some line like this into a magnetic state. And, these higher, I should not even show that. They basically put me in metallic regimes where this whole picture sort of breaks down.
It's a non-interacting medium. So
Yeah. But then, you... J
should be 0.
Yeah,
right?
J is 0. But as I said, we are, you have to look at, in that case, you should really be starting with a band picture.
Yeah.
And you can't just write down the atomic picture in that regime.
I had some question about vacuum antipodia. So the two sides. Just that the lambda is small. I think that your cognac could be derived, that you can all spin off the summary derived just.
Okay, so first thing let me point out real quick, two things. First is that this the book by a set of lecture notes by Peter, which were sort of recommended, is not in the library, I think, but there is an online copy. If you Google it, you'll find it. second is that the syllabus for today seems to be a little bit off. It's saying that Jacob is going twice. In fact, Jacob and Maya today. Jacob and possibly on Wednesday. Okay, so what are we talking about today? So for 2 weeks now, we're going to discuss Ricci curvature. The various aspects of it. So, I'll outline for you today more or less kind of what I want to cover over the next couple of weeks. But maybe a good place to start before I get into any of this is just to sort of say pairs. So I mean, Ricci curvature, it's a fairly popular topic right now, but why? I mean, what's the motivation? And there's a lot of motivations coming from different directions, but if I were going to give you sort of a 25-word or less reason as to why one studies Ricci curvature, I would start with the following. I would start with just let's look at curvature, right, before anything. I mean, I'm kind of hoping that we all know what a Riemannian manifold is, so I can just say that's a Riemannian manifold. So if we have a Riemannian manifold, what's the curvature? I mean, I can give you a definition. It doesn't help you much when you see it the first time, but you can give it. So, I mean, if the curvature is it's a 3-1 tensor, right? So it means that if I take 3 vectors, it gives me a vector. And it does it just by looking at the Hessian, the xy direction of C, and subtracting off the Hessian and the y-x direction. Of course, when you put it in space, this is 0. On a general Riemannian manifold, it is not. And so you simply write the thing down, and you define that as being curvature. That's curvature. Now, that's a useless definition. I mean, it doesn't tell you anything. Right? I mean, it does sort of, it tells you everything important about the geometry, but why is not so clear to me. And in particular, I mean, I'm an analyst, and most of what we'll be doing for 2 weeks in here is geometry and analysis. So why on earth does this have some sort of relation to analysis? And just from a moral perspective here, the point is this. How should you view this thing? I mean, it's a 4 tensor, right? You should view this thing as being the Hessian of the metric. Right? So it's like you take a function, you take 2 derivatives of it. This is like taking the metric, Gij, and taking 2 derivatives of it. Now, of course, if you actually take the Hessian of the metric, you get 0. This isn't a literal thing, but one should view this from a moral perspective. In particular, if I hand you a Riemannian manifold and I tell you the curvature is bounding, then you should expect the metric. But now, if you look at Ricci curvature, okay, definition. What do? We take some orthonormal bases. I and so this is to say we trace the curvature is the Ricci. But now, I mean, if we're viewing the curvature operator here as being the Hessian of the metric, then when we go taking a trace, it's only this is telling us that we're viewing the Ricci curvature as being the Laplacian of the metric. And this is very much true. And in particular, I mean, this should, I mean, basically with no other words said, this should give some motivation as to why Ricci curvature appears everywhere. I mean, the very first thing you do when you start analysis is trying Laplacian. They appear everywhere, math, physics, whatever. So it's not surprising that if you want to study Riemannian manifolds, that what counts as the Laplacian of the metric should appear everywhere. It does. It's basically false. Actually interpreting this as crossing the metric is more tough. The problem is that you can really legitimately make